Hello, my name is Carla, and I'm here to present you our project entitled Optimization of Agricultural Management for Soil Carbon Sequestration using Deep Reinforcement Learning and Large-Scale Simulations. This project was a joint work between University of Illinois in US, KTH, Stockholm University, the Applied Research Institute from Portugal, and University of Tasmania in Australia. The idea of this project was triggered by the challenge of feeding an increasing global population, which is expected to reach more than 9 billion people by 2050. Although total food production has been growing and is expected to continue to grow, there is a gap between the current productivity and the required to feed the future population, especially in low-income countries where the current production rate is projected to be about half of that is required to feed the 2015 population. The challenge of feeding an increasing population is exacerbated by limitations, for example, on agricultural land, which is expected to slightly increase and even decrease in developed countries associated with the lack of space. This implies a 60% increase in the yields per acre to feed the future population. Climate change is another highly relevant challenge given the increasing frequency of extreme events such as droughts and floods. And we will have to account with an increasing competition for natural resources such as water, which is expected to increase for irrigation purposes, especially under a warming climate, but also other resources such as mineral fertilizers, given the global decrease of these resources. And there is even an additional challenge of producing food of good quality to feed all this population. So this project aims to maximize crop yields and mitigate climate change impacts in croplands by developing an intelligent agricultural management system using deep reinforcement learning and large-scale soil and crop simulations, and to support policy by improving sequential decision-making regarding best agricultural management practices. To achieve these aims, we developed an intelligent crop management system that generates deployable and adaptable management policies based on reinforcement learning, imitation learning, and crop simulations via the SAT model, which is one of the most widely used crop models to simulate the crop and soil conditions under different management practices, basically. The developed framework is a combination of reinforcement learning on crop management and imitation learning on solving the problem of partial observation given an expert policy. We first use deep reinforcement learning, in particular deep key network, to train the management policies that require all state information from the simulator as observations, which we call full observation. And we then invoke imitation learning to train management policies that only need a limited amount of state information, which can be readily obtained in the real world. For example, like rain, temperature, or the different plant growth stages. This limited state information is denoted here as a partial observation. In a bit more detail, in our project, we consider that by viewing crop management as a sequential decision-making problem, we apply reinforcement learning to find the optimal crop management policies from simulators. In this case, we use reinforcement learning-based policy training with different reward functions that represent different trade-offs among crop yield, namely nitrogen fertilizer use, irrigation water use, and environmental impact in terms of nitrate leaching during the crop growth cycle. Then we leverage imitation learning as a new tool to find the optimal management policies that require only observable variables that can be easily obtained or measured in the real world. The imitation learning seeks to learn a policy by imitating the behavior of an expert, which in this case means by mimicking the actions of the previously reinforcement learning trained policies under full observation. The imitation learning trained policies can be deployed in real world since the policy only requires observable states from the environment. In this project, nitrogen fertilization and irrigation management are formulated as a finite Markov decision problem. On each day, the agent receives the state of the environment and chooses the action from the action space A based on some policy. The state of the environment contains information related to the weather, plant, soil at a given day from the simulator. The action consists of the amount of nitrogen fertilizer input represented in the bottom equation by NT and the amount of irrigation water represented by W to be applied for that day action, so that the reward function is defined by the equation shown on the screen where W1, W2, W3 and W4 are 4 weight factors to be determined. Epsilon is the yield at harvest and NLT the amount of nitrate leaching at a given day. The proposed framework was validated using the maize crop with 2 case studies, one in Florida, US, and one in Zaragoza, Spain. For each case study, we used a deep key network, as I mentioned, which is a deep reinforcement learning algorithm selected for agent training to learn the optimal policy that maximizes the future discounted return. Again, the trained policies are then used as the experts to train management policies under partial observations using imitation learning. We test the performance of all the trained policies in simulation and compare them with 2 baseline policies. The baseline policy of the Florida case study follows a maize production guide for farmers in Florida, written by domain experts, and the baseline policy for Zaragoza case comes from the survey data on real-world management practices of maize farmers. 5 different functions for the reward calculated from the previous equation were used to train the reinforcement learning agent, and we achieved 5 different trained policies for each case study. The parameters used in each reward function are listed in the table on the right side. The reward function 1, for example, represents the economic profit that the farmers gain based on the approximate price of maize and cost of nitrogen fertilizer and irrigation water. The reward function 2 to 4 indicate the economic profit under different situations. Reward function 2 represents the extreme case when irrigation water is free. Reward function 3 denotes the extreme case when nitrogen fertilizer is free. And the reward function 4 simulates the situation when the price of nitrogen fertilizer is doubled. So compared with the reward functions 1 to 4, which consider economic profit only, the reward function 5 also includes the additional term of nitrate leaching, which is a major cause of environmental problems, including eutrophication of water resources and soil degradation. Given the 5 different reward functions shown on the right, we achieved 5 different trained policies, and each trained policy X is trained using the reward function X. The table in the left shows the amount of fertilization, irrigation, and nitrate leaching, as well as yield, following each policies, and their corresponding calculated cumulative reward using each reward function design. The results of all the trained policies under full observation show that the reward function affects the strategy of the trained policy significantly for both cases in Florida and Spain. For example, trained policy with the reward 3, which regards to a zero cost of nitrogen fertilizer. The trained policy applies a large amount of nitrogen fertilizer compared with others to achieve the highest yield and the largest cumulative reward with a small amount of water. In all the cases, the reinforcement learning trained policies outperform the baseline policies for both case studies. With the imitation learning, the policies were trained by imitating the actions determined by the experts, which are the previously reinforcement learning trained policies under full observation. We ran the simulations by the expert policies to create the demonstrations and store the generated pairs of observations and actions. The results show that the imitation learning trained policies outperform the baseline policies for both case studies, and that under partial observation, the imitation learning trained policies achieve similar results compared with the reinforcement learning trained policies. So to conclude, basically we present an intelligent framework for crop management, specifically nitrogen fertilization and irrigation, based on deep reinforcement learning, imitation learning, and crop simulations using the SAT model. The generated crop management policies can adapt to different locations and objectives and are directly deployable in the real world. Simulated experiments conducted on maize crops demonstrate that there is a superior performance of the proposed framework compared with the conventional management practices. And this project also demonstrates the potential of deep reinforcement learning in optimizing crop management for more sustainable and resilient agriculture. So, thank you very much for listening to this video presentation. If you have any question or want to discuss the topic, please contact us through the email previously shown. Thank you very much.